This is on driving algorithms and software development to optimize deep learning models, inference, including LLMs, vision language models, and diffusion models on NVIDIA's latest platforms. He has over 11 years of industry experience in efficient deep learning across his career from NXP, Xilinx, Baidu, and OmniML, which was acquired by NVIDIA. So Zhiyu has a record of over 30 published papers and patents. He holds a PhD degree in ECE from UIC with a thesis in the field of information theory, and then the extra added information is he was my third PhD student. So he worked with me on very theoretical, transactions on information theory papers, okay, in multi-user information theory, and then made this switch, and he has just had a wonderful career in the Silicon Valley. I have unbelievable, yeah, I'm very proud in some sense. I have nothing to do with it, but the ability of him to switch directions and just to be agile, you should talk to him and hear about his career story, okay? It's fantastic, it's fascinating. And I'm very, thank you very much for making the trip over from the Bay Area to talk to us.
Yeah, thanks, Professor Natasha DeRoche's introduction, and thanks for inviting me to here. Yeah, I'm very glad to present our work on something deep learning optimizations here at the Northwestern University at the IDEO workshop, efficient learning, machine learning workshop. So today I'm going to introduce the FP4 quantization, which is floating point 4-bit quantization and its real-world applications on LLMs and diffusion models. Okay, here's the disclaimer here. Okay, the talk is not endorsed by NVIDIA. That's all opinion expressed are those of the speakers, not NVIDIA. Okay, let's get started. The outline. So I will first introduce the quantization in deep learning and also introduce the FP4 numerical format, especially on NVIDIA Blackwell GPU, which is the latest generation GPU offered by NVIDIA. And next, we go to the workflow of PTQ, post-training quantization, and quantization-aware training, QAT, for FP4 quantization. I will introduce the language model and diffusion model and which part we want to quantize and which part cannot be quantized. Along the way, I will introduce some results on the accuracy and also the performance. Performance means the latency or throughput when you quantize the model to 4 bits for both language model and diffusion models. And the last part, I want to introduce a software stack offered by NVIDIA. This is my team working on. It's called TensorRT Model Optimizer. It's a software library to enable users to do quantization for large models, like diffusion models and language models. We'll look at the overview of the software stack and overflow and its APIs. And I'll also briefly introduce how we deploy the quantized model via downstream framework like TensorRT LLM, SGLang VRM, and VRM. These three are very popular open source framework, inference framework to deploy the large language model and the vision language model. Okay, introduction. So what is quantization? So we say in deep learning, quantization is to reduce the numerical precision for model parameters and activations. And we want to use quantization to optimize the memory usage and achieve better computational efficiency, but also maintain the accuracy. Right? And why quantization is important is reduce model size, enabling deployment on edge devices, which usually has constrained resources, and speed up the inference by using low-bit arithmetic, and we have low-bit like math kernels on the hardware to achieve the speed up. Also, we want to lower the memory bandwidth and decrease energy consumption, making AI more sustainable. And the picture on the lower right is a typical diagram for quantization. So basically, for example, if you want to quantize a floating point numbers, like ranging from range R min to R max into an integer numerical format. That's from like Q min to Q max. This is a standard symmetric quantization, and you have a scaling factor S here floating point scale. So mapping the numbers in the from the floating point range into the integer range. And for generative AI, we typically using quantization for large language models and diffusion models. Okay. Numerical format. So what's the numerical format of FP4? In this talk, I will mainly focus on NVIDIA's FP4 numerical format, which is E2 and 1, which means in the 4-bit representation, you have 2 exponential bits, 1 mantissa bit, and 1 sign bit. The maximum value of this representation is 6. And there's a table, and I won't introduce the table, but you can think of that the numerical range from this NVIP4 format is minus 6 to 6. And we use double scaling for NVIP4 format, which means there are 16 elements share a dynamic E4M3 per block scaling factor. E4M3 is the format of floating point 8-bit numerical representation. So that means 1 sign bit, 4 exponential bit, and 3 mantissa bit. And for each, for the block scaling factors, they also share a static IP32 per tensor scaling factor. So there are 2 levels of scaling. One is the global level, which is the IP32 global level per tensor scaling, and also a more fine-grained per block scaling factor, which is in IP8 format. And the benefit of the NVIP4 over IP8 on Blackwell is obvious. So we reduced 8-bit position to 4-bit position. So that means theoretically we can achieve 2x memory bandwidth saving and 2x max throughput on NVIDIA Blackwell tensor cores. In this talk, I will refer NVIP4 and FP4 in this talk. Let's look at the comparison of the IP4 with other formats. As I said, we will focus on NVIP4 in this talk, but there's another common IP4 format called MX IP4. This is proposed by Open Compute Project. OCP is the organizations across the industry, semiconductor industry. There are committees that they study the positions of the data and for machine learning, which one is how to define the low bit positions. So they propose an MX IP4 format, which is also a E2 and 1, but the difference from the NVIDIA's Blackwell NVIP4 format is that they use block size 32 and E8 and 0 scaling factor. And there's no double scaling. They use single scaling to quantize move the from high precision to low precision. And E8 and 1 and 0 means that all bits are in exponential. There's no mantissa bit. And block size 32 is different from the NVIP4, which is using block size 16. The advantage of NVIP4 format, so we use 8-bit block scaling factors. So that means less overhead and more fine-grained compared to IN4 format. IN4 usually use a much larger block size, like 128 or 64, because it has less representative power to present the. So NVIP intend to prevent large range of the numbers compared to IN4. So we have we have 8-bit blocking scaling factors and smaller block size. And this allows for double scaling, so we can represent larger dynamic range, and also native hardware support. So this is supported by the Blackwell GPU, which is the latest one offered by NVIDIA. And IP4 format on data presentation is one of the key features in Blackwell. Okay, so here is the how we define double scaling. There's some equations here. So what is the block scaling factor? It's calculated as the block scaling factor, which is before the IPA quantization, and divided by the per tensor global scaling factor, and cast it to IPA format, E4M3. The global level per tensor scaling factor is simply the A max, which means the maximum value in a tensor divided by 448 and 6. And 448 is the max number of the IP8 data position. So we just take the maximum number of the XP8 format, 448 times 6. 6 is the max value of the IP4 format. So I think this scaling factor is quite straightforward. So to take the max value of the tensor divided by the max value of the IP8 times the IP4. And block scaling factor is just also take per block, take the maximum value divided by 6, which is the maximum value of the IP4 format. Okay, up to here, any questions? Okay.
Is there any impact on performance through quantization?
Good question. I will go through the results later, using FP4 quantization. Okay, so let's first look at the large language models, FP4 inference. Okay, here's the typical block for transformer. So I assume people here are familiar with what is a transformer. Basically, it's a foundational building block for all the large language models. So for transformer block, typically it can compose of two parts. One is an attention block, which is composed of a few layer norm layers and also QKV projection layers and batched matrix multiplication layers and softmax. This is a very typical attention block. And also the MLP block, multi-layer perception block, it also consists of a layer norm layer and two fully connected layers with a RALU activation layer in between. So what to quantize in a transformer block? Let's simplify the layer and focus on attention block here. And you can see that from this picture, the small yellow circle here is the tensors we want to quantize. And we have three quantization targets. GEM, which is the general matrix multiplication mass, which is typically in FC layers, fully connected layers. And also we have QV cache here. QV cache is the kind of you caching the intermediate results when you do the inference. So especially for long context, you want the network to memorize some previously computed results, so we don't want to compute it again. This is typically used in large language models, and also multi-head attention, which is BMM layer here. When the context length, say the input token is small, then FC layers usually takes the most of the compute and the most of weight. But the trend is people getting more and more longer context, so QV cache is become larger and larger. So QV cache quantization is become also important to quantize. I will talk about QV cache later, but let's focus on the regular blocks to be quantized for now. Okay, this is the typical how we quantize a transformer block in for language models. And the question is about how this IP4 quantization performs in real language models. We can look at some typical models and then look at the benchmark. So here we use IP4 to quantize both weight and activations in the large language model. We have three models here, which are all very recent, popular, open-sourced large language model. Llama 3.1 for 5B, 3.37B, and DeepSeek R1. Let's look at the IP4 results compared with INC8 and IP8. So if you quantize network to INC8 and IP8, which is the blue column and yellow column here, and IP4 quantization represented here is the green column. And you can see that IP4 quantization achieved almost similar to the IP8 result for larger models. 4.5B is a very large model, 4.5B billion parameters. For smaller models, usually it's more sensitive to quantization, which makes sense because smaller model has less redundancy. So it's very sensitive to quantization. So you have some accuracy drop here compared to FP4. But surprisingly, if you compare it to int8, the 4-bit precision floating point in the FP4 achieve almost the same accuracy with int8. So this is very promising results here to show that even for smaller models, FP4 can achieve same accuracy with the int8. And DeepSeek R1 also are very large models. Any questions?
Yeah, I have a question about this table. For this result, the quantization part is realized by which kind of PTQ algorithm? Is like AWQ or GPQ like?
Oh, okay. I'll talk AWQ later. This is for the default NVIDIA quantization,
So like
double scaling, and there's take the not around. Let's take the A max. So just find the A max and then using the double scaling to do the quantization. There's no fancy algorithm. This is the native supported FP4 quantization. Okay, and then look at the, if you compare with the weight only and int4 weight only quantization here, you can see FP4 is better than int4. Yeah, so this slide shows basically we can achieve quite good results on language models using FP4 quantization. And the benchmark using MMU, which is a very common used benchmark for to evaluate large language models. It's not the only one. There's a lot of benchmark. We pick MMU, 5-shot. It's no chain of thoughts because it's a commonly used benchmark to compare the accuracy. And we have other benchmarks as well, but MMU is a good representation here. Okay, the question about AWQ. Yes, in our FP4 quantization, we also leverage the AWQ algorithm, which is the activation-aware weight quantization. It's a PTQ algorithm designed for weight-only quantization. So the idea is you instead of look at the weights, you look at the activations and figure out which channel in the matrix is more important. So this figure shows basically we want to scale up the important weights. Say the deep blue row here means the important weights. How we figure out this is important? Instead of looking at weights, we look at the activations. So this column, the deep red column, represents the important weight. Basically, the has higher magnitude, which means more important. And we look at activations. Say this column is important activations, which maps to this row in the weights. We figure out this row is important, and we have an alpha here to protect this important weight. Alpha is learned, trained and learned. So how much we want to scale up the important row here in the weight is what the algorithm do. So scaling factor, Sx is a scaling factor for activations, and we have the optimization loss function here to train the alpha, to find the best alpha that to protect the important or salient, salient weights in the matrix.
Salient just means large size?
Higher magnitude.
Higher magnitude.
Yeah, important weights. Yeah, salient. Yeah, this paper I think is the best paper in last year's MLC's conference. It's from Song Han's group. They specialize in this. Question?
The result that you showed in the previous slide, was it for the PTQ? Or was it for the post-training quantization? This result.
This one?
Yeah.
What's the position for what?
Did you use the quantization for the post-training quantization, or just it was the quantization over training part?
Oh, this is just PTQ.
PTQ, right?
Yes.
Okay, and you only considered it for the attention, right?
All the linear layers here.
Oh.
All the linear layers is quantized.
NLP as well, right?
Yes.
Oh.
Yeah. Okay. So the AWQ algorithm is originally designed for weight-only quantization, but we applied that algorithm on FP4 weight activation quantization as well. So surprisingly, AWQ also works well for NVIDIA. The insight is salience weights or activation channels can be scaled up to facilitate quantization. So like I said, we learned the alpha to protect the important weights. And auto-adjusting the pre-quant scale, which is basically the alpha to balance the quantization difficulty in weight and activations. If we print out the layers, the two layers here in a language model, and you look at the best pre-quantized scale, you can see that's different at different channel index. They are very different. So the red column means that it's more important, right? We want to scale up that weighs more. And also in some layers, the pre-scale quant scale is very small, which means it's less important. So for this layer, MLP down product layer is less important than the self-attention Q product layer. They're very intuitive here. So we want to protect the important weights. Okay, we talk about PTQ. Regarding the QAT here, the quantization aware training. So the nice part of PTQ, there's no training involved. You only need to do the calibration, so less computative intensive. But if we still see NVIDIA compared to the baseline like BF16 or IP16 formats, there's still accuracy drop. If we want to further bring up the accuracy, we need to do QAT. A simple but yet effective QAT method is Zhiyu estimator. What does it mean? It means that, so look at the regular training. There's a tensor here and operator here. Operator means that you either do like matrix multiplication or convolution. You do the forward pass, you back propagate the gradient back to the tensor. But when you do QAT, you can now directly back propagate the gradient into the tensor because there's a quantizer here, which is cannot be it is not differentiable. So you cannot directly back propagate the gradient into the tensor. So which means the tensor needs to be kept in the original position, and we use the STE to estimate the gradient and back to the original tensor. This is, I think, very standard QAT process, and is very effective. We can show some results for QAT as well. Here we look at two NVIDIA internal models, and not internal, it's also open source, but developed by NVIDIA. The Nemotron 4 15B and Nemotron 4 340B base model. Baseline here is 62.4, for example, here, and PTQ is FP4 and dropped about 3.2% accuracy. But when you train with the reason why we picked the Nemotron model is because we have the data to train the model to bring back the accuracy with QAT. For open source models, because those data are not, we don't have those data, and we have to use synthesized data to do QAT, which is not ideal for QAT. So QAT prefer to use original training data to train the model. So if you use synthesized data, then the accuracy will not perform well compared to if you use the original data. This is also a very important observation we found after all these experiments. So we picked the internal model because we have the training data. So after the QAT, you can see that accuracy is bring back to this one even a little bit higher than the original baseline. So this one also the same. So yeah, so very surprisingly, even you use 4-bit to present the numbers in the language model, you can achieve the same accuracy with the original 16-bit. And here, here we only use the 5% of the pre-training data. So QAT is not that costly, right, compared to the pre-train. So only 5% of data is used. Question?
Yeah, I have a question about the previous slides. This FP4 with QAT setting is like a fully quantized QAT, or like the DeepSeek FP8 fully quantized training.
What do you mean fully quantized?
The fully quantized training.
fully quantized.
The DeepSeek paper, they use the FP8 training.
Okay. That's
it's
different.
So-called
Okay.
fully quantized
I see.
QAT. This FP setting,
Right.
it's the
No,
FP4.
it's for training. We still keep the like I showed here. We keep the weights in the original position, so we don't do IPA training. Its training is still in the
so the gradient
IP16.
and the
It's different.
Yeah, it's
In
all
all,
FP4.
yeah, in this talk, we only focus on inference. So IP4 quantization for inference. Training is another story. So it's not covered in this talk. Yeah. But I can tell IPA training done by DeepSeek is very promising. And there's a trend to use low position training as well in the industry. We also study IPA training. And even for now, we also study even IP4 training. We are doing some exploration work.
Yeah, we also have some study about the FP8 training or FP4 training. We can talk later.
Sure. Yeah.
Sorry.
Oh, another question.
What do you mean by 5% pre-training data is used? What do you mean?
Sorry, I cannot hear.
What do you mean by 5% pre-training data is used?
Oh, 5% for training data.
Quantization, you don't use whole data, you just use 5% of data set?
Yes. Randomly sampled from the original pre-training data set. We only random sample 5%.
And why does it need less data set? In
Because-
quantization?
Yeah, because we found 5% is good enough for QAT. So basically, QAT, you're training the QAT is you're trying to find the best Amax to quantize. But that's different from you training the whole network. And we don't want to use the whole data set because that's too costly. Yeah. Okay, so look at the performance. So when we say performance here, in like semiconductor industry, when we say performance, really means the speed. So speed means like either latency or throughput. This is the initial data we can show here. There's more data is ongoing internally. But you can see Llama 3.1 70B and 3.1 405B and Mixtral is the MOE model. TP1 means the tensor parallel size, TP1. Because 405B is too big, so we have to use TP8. Compared to the previous generation GPU H200 IP8, which is the gray column here, IP8 achieved for Mixtral 2.4x, 405B 2.3x, and 70B 2.8x. So it's very decent speed up. Again, this is for inference. And so when you do inference for the model, you achieve very good speed up with IP4. So that means you can achieve almost the same accuracy with IP4, but come with a very good speed up. Okay, mixed layer position. So I think previously we talked about a straightforward quantization recipe, which means you quantize all the layers with the same format. But people may ask, can we do better? Can we do more fine-grained? So for each network, there's a lot of many layers. Is this optimal to quantize all the layers with the same position? Can we achieve better accuracy with mixed layer position quantization? So we offer the auto-quantize algorithm, which basically aims to figure out which layer is more sensitive and which layer is less sensitive. For less sensitive layers, we can do more aggressive quantization. For more sensitive layers, maybe we just do not quantize because it hurts accuracy. And usually the LLM hat, the last layer in the network, usually is very sensitive. So we usually don't quantize the LLM hat layer. And we can manually select which layer is we don't want to quantize and we want to quantize. But that's not ideal. Right? So we have the auto-quantize algorithm. This is internal in-house developed algorithm to quantize the large language model. For auto-quantize, we look at a proxy to estimate the accuracy intact. So you look at each layers for different positions, like NVIP4, IP8, or don't quantize. What is the sensitivity? We have sensitivity score to evaluate for each layer. How much sensitive is this layer? And the sensitivity score is calculated by backpropagate the gradient. So we do backpropagation when you profile the network. We use the Hessian matrix. The Hessian matrix is the second order gradient. Second order differentiated. Look at that value, and then we calculate the sensitivity score. And cost here is basically means the after the quantization, what is the size of the network? So larger the size means the higher the cost. So we want to minimize the cost given a target. Say user provide a target, say we want to quantize this to reduce the size of this network to, for example, 4 billion. And then we run our algorithm and run the profiling of the network that we want to achieve that target. So we can say this layer can go to 4 bits, this layer go to 8 bits, but the total size of the network should not greater than 4 billion, for example. This is the result showing with auto-quantize how the accuracy looks like. We pick 4 popular open source large language models. The green line here means the default FP4 quantization. So we only quantize the MLP layer, linear layers. And auto-quantize is the blue curve. Effective bits means basically, in average, what's the bit width for the model that is quantized. Here is we evaluate on MLU. You can compare with the default IP4 quantization. Auto-quantized, because you do mixed layer quantization, you achieve higher accuracy. Here, very informative. So we say auto-quantize achieve better quality than human heuristics. Okay, I think we have. I think we should go faster here. So I don't want to go to too much detail for advanced topic. Basically, for quantization, you can do straightforward default quantization recipe, quantize all layers with the same quantization formats. You can do mixed layer. You can also do mixed tensor. So which means in the quantization attention transformer block, you can do now for IP4 you do actually weight 4 bits and activation 4 bits. So it's called W4A4 quantization. But you can also do mixed tensor. You can say usually activation is more hard to quantize. So people intend to keep the higher position for activations. So we do weight quantization in 4 bit, but activation we quantize to 8 bit. So that's W4A8 quantization. In our software tool, we can enable, or we support that mixed tensor position quantization, and also KV cache quantization and BMM quantization. This is given when you need KV cache quantization and BMM quantization, especially when you have long context. Long context means you have very large KV cache that take a lot of memory, and you also want to quantize that portion. BMM layer is more difficult to quantize because it involves non-linear operation here, softmax. Softmax we usually don't quantize, but the output of the softmax we can quantize to 8 bit. All the yellow circle here means that we can potentially be quantized. Okay, takeaway here. IP4 PTQ, there's no training, just calibration. For linear layers, already achieve very good trade-off for model size and single batch inference. And AWQ algorithm improves IP4 PTQ accuracy, and pre-training QET can recover accuracy of IP4 even further. And auto-quantize provides fine-grained layer selection for that can beat the heuristics. Okay, before that, any questions? Next, I will talk about diffusion models. Okay.
I have 2 questions. First, about the auto-quantize. So you said that the more sensitive the linear layer is, the higher level of quantization you consider, right?
Higher level of quantization. Yeah, auto-quantize want to find the optimal way to to quantize network, say which layer is more sensitive and which layer is less sensitive.
The more sensitive it is, then, for example, you assign 8 bits, right?
Yes.
So
The more sensitive, assign 8-bit or even don't quantize.
And so, for example, mixed precision, you consider the variety of, for example, 4 bits, 8 bits, and no quantize?
Yes.
Something like
Yeah, depends on the recipe. You can also like use here example is IP4 and IP8. You can also do INT8 or INT4 AWQ, all those recipes. Yeah. This is just an example here. Okay, diffusion models. Okay. Diffusion model is a very popular generative AI model that can generate image or videos. FluxDev is one of the state-of-art image generation models developed by Black Forest Lab, which is a startup, I think, in Europe. So we profile this model, and so the structure, the architecture of the FluxDev model is that we have a transformer backend, and also we have a T5 encoder and clip, which do the mapping from the text prompt to the latent domain. So translate the prompt into the latent domain. And we have a VAE here to transform back from the latent domain to the image domain. And the transformer backbone here, the DIT, diffusion transformers, is the most it takes the most part of the overall latency. You can see that transformer takes around 98.7 of the latency in 5090 GPU. So for quantization, we only focus on this part. So this is about a software stack. So we do quantization on the torch level. After the quantization, we export the Onyx model, which is an intermediate graph representation of the network. From the Onyx model, we can build TensorRT engine that can be fit on the NVIDIA GPUs. So we run the inference on TensorRT engine, which is optimized engine for running inference. They have a lower level kernel to fuel some operations, so you can achieve faster inference. This is the typical flow for IP4 quantization. So quantization done on torch flow. After quantization, you export Onyx and then build engine, run inference. Okay, QAT and SVD quant. For IP4, we found that for image generation, doing only IP4 depend on the recipe. If you're less aggressive, you keep some layers unquantized, you can achieve good results. But if you go more aggressive, you need the QAT to bring back the accuracy. And SVD quant is another popular, very recent quantization algorithm, also from Song's team. He developed this their team developed this algorithm to bring back, to improve the accuracy. Basically, compared to QAT, SVD quant is a PTQ algorithm, but it can achieve very good accuracy compared to QAT. SVD quantization explanation, right? The SVD quant is a single regular decomposition quant. Basically, it quantizes the tensors to be two parts. One is the gem. You use the gem to calculate basically for the matrix multiplication, and you have a LoRa layer. LoRa basically is a decomposed lower rank branch that can be trained to bring back accuracy. Yeah, for QAT, actually we can only focus on the LoRa part, and the gem part we use the regular IP4 quantization recipe to quantize. Distillation is QAT. So original QAT that does not perform well for the FluxDev model is because we don't have the original training data. If you use synthesis data to train QAT, the result is not ideal. That's why we figure out another way to do QAT. It's called distillation. Some people call it QAD, so quantization-aware distillation. Basically, you use distillation technique to have the teacher model, which is in full position, and student model is the quantized model. You learn from the full position model during the quantization-aware training process. Either you do output distillation, so you only compute the very output layer to compute loss. You can also do blockwise distillation, which means after each block you calculate the loss. Okay, here's the results for image generation on the Flux model, BF16 and IP4 PDQ, IP4 QET, and IP4 SVD quant. Qualitative results, look at the pictures, you can see the detail that the letters in the laptop in the screen is it still has variations from the baseline, but the SVD quant algorithm achieve better, like the letter looks more clearer than the other tools compared to the baseline. And in general, if you look at the docs, it's almost the same. So even 4-bit can achieve good result qualitatively. If you look at the quantitative evaluation benchmark, image reward, clip, IQA, and clip, you can see the numbers here. QET and FSD quantization achieve better result than the PDQ. And compared to baseline, they almost bring back the full accuracy. This one a little bit job. But yeah, the message is here that you can do 4-bit quantization for image generation model as well, and the accuracy is pretty good. And performance, latency or throughput, you can see IP4 achieve like 1.7 speed up compared to IP8 and 2.9 speed up compared to original IP16 position. And for video generation, we also do experiments. We use Cosmos MV as the baseline model. It's NVIDIA's word foundation model, which is use text prompt to generate videos. This is a frame extract from the generated video. You can see that IP4 PDQ and IP4 SVD quant achieve quite good results compared to the original BF16 model. Okay. Any questions? I think I will quickly go through this, given the time. Okay. TensorRT model optimizer and quantization. So this is our team that focus on that we want to build a software stack that user can use to conveniently quantize the models. It's open source. It can easily install by pip install. And it's on GitHub. Feel free to check. And the offering of our software stack, so we are not only do quantization, we also have distillation, sparsity, pruning, speculative decoding. This is all popular model optimization technique that can reduce the redundancy of the model and achieve speed up. And quantization format, we support all popular low position data format. And IP4 is the new Blackwell. Workflow, okay. So we start with the PyTorch model, and we do calibration and quantize using our MTQ quantize API. And we export that quantized model into a checkpoint, either in a Hugging Face checkpoint or Onyx graph. And then we take into the downstream inference framework to deploy that quantized graph. For language model is TRT-RM, VRM, and SGLang, and for image model we use TensorRT. This is our software stack. You can see that very, very easy to use API. You just provide a calibration data loader, usually like random sample from training data set, very small one. And you provide a forward loop to run through the network, given the data, run through the model, and use mtq.quantize API. You only need to provide the recipe. So IP4 default config is the default quantization recipe for IP4. And you give them a forward loop and the original model, and you quantize the model. Very easy to use. And like for the QET, first you do the quantization, do the PDQ, and then you want to retrain the quantized model. You simply you can leverage the original training pipeline. So give the model, the PDQ model, and data loader, and the loss function, and you can start to train. And this is the last slide. So after the quantization, how we bring down the, how we take that quantized model into the production. For this, we need the downstream inference framework. SGLang, VRM, and TensorRT-RM are all three frameworks that are very popular in open source. TensorRT-RM is developed by NVIDIA, and SGLang, VRM, all open source framework, and initially from the Berkeley lab. Here's the example. use model opt to quantize the model. And you can see this line. This is an example for SGLang, and similarly for the other two. The API looks quite similar. NVIDIA Llama 3.1 AP instruct IPA, which is quantized checkpoint from model opt. And then you just give this line and specify quantization is a model opt. In SGLang, it can build the engine and run through SGLang backend runtime. And you give the prompt and then generate the output. Yeah, very straightforward. Okay, summary. So we introduced the FP4 quantization and leverage Blackwell GPU and for accelerated inference for generative AI models. And FP4 inference deliver very good performance on both LLMs and diffusion models. And TensorRT optimizer enables seamlessly inference optimization, including FP4 quantization. And we work with ONS open source community to integrate our software stack to to achieve good speed up for users when they run the large language models. So for NVIDIA, we provide a platform, and we work closely with the open source community to enable them to better use our GPU. That's our goal. Yeah, I think that's it. Any questions? I think it's about good time, right?
Yes, perfect.
Is the auto-quantize mixed precision algorithm a published work, or is it integrated into the API later as well?
It's integrated into the API, yeah.
But it's not published.
It's open sourced. That part is not open source yet. It's compiled, but we plan to open source as well. And auto-quantize is, I know there's some other software stack also use similar ideas for auto-quantize. But our software stack is currently not open source, but will be open source. Yeah, our goal is at NVIDIA, at least for our team, we build software stack to enable the better use of hardware. So we don't sell software, so we just open source. We will plan to open source.
So I was curious if you want to think of a theoretical model for kind of quantization, just to understand when you can prove that this quantization doesn't affect the quality too much and so on. Should I really be thinking of these as random? You're basically rounding things, right? Should I think of these as being random errors, or is it not very realistic, and you really need to think of these as potentially arbitrary precision errors that arise when you do this kind of low precision rounding?
Okay, so the question is how to it's randomly selected. How to randomly select layers, or
No, I guess quantization, in some sense, at a basic level, you're taking some number which has which has many bits of precision, and you're chopping it off to just the first 8 bits or something, right? And that's a rounding error.
Not the first 8 bits. It really depends on numerical formats.
Sure, whatever it is, right? But there's some round off error that's coming in,
right.
And to some extent, what many of these successes are showing is that maybe it's not, these round-off errors are not contributing too much to the
very good
accuracy.
Yeah.
I'm just wondering if those errors are somewhat random looking. If you want to think of a theoretical model to understand the effect of these kind of, precision errors, should I be thinking of these as random errors, or should I be thinking of them as arbitrary worst-case errors?
I would not say it's random error. So if you print out the distributions of all the weights or activations, you can check that which layer or what kind of distribution it looks like. Like you said, for most of the large language model and diffusion model, we found the outliers, the one that is very high magnitude, is not that sensitive. So sometimes we just clip that out. So we just don't use that value, just clip out. And then we found that especially for very large models, like 4 or 5B, DeepSeek, all those extremely large models, it's worked pretty well. But for smaller model, like 8-bit, sometimes, it's introduced higher errors. You can see actually drop. But I would say that's not, it's mostly based on experiments to see that error is not very sensitive. We can deal with that. And also, not all layers is quantized, right? So we still found that some layers is really simply, for example, softmax, you cannot do like 4-bit for softmax. That's non-layer, linear layers. Yeah, we keep that layer unquantized. Question.
On the quantized message, why do you use Hessian matrix to choose sensitive layers?
Use Hessian matrix to choose what?
To choose sensitive layers. How do you use Hessian matrix to choose sensitive layers? And why do you use Hessian matrix?
Yeah. Okay, that's a good question. For using a second-order derivative Hessian matrix, we found that because it goes through the backwards, it's a back-propagate gradient. So we have a proxy score, and then when we update the weights with second-order gradient, we calculate, we auto-run forward. We look at that score, and then depending on the score, we pick which layer, we understand which layer is sensitive or not. Yeah, actually this, it's not, I think in research community, it's not like that novel, right? I think for pruning or NAS, neural architecture search algorithm, when we do pruning, people also use this second order degree gradient to like you first have a proxy score, and then you look at the score using calculate by backpropagate the second order degree gradient, and then you select which layers and how much you want to prune the model. Yeah, it's I would say it's not very new, but it's worked pretty well. Yeah.
Last one.
Okay. So, is the effectiveness of the quantization actually applied only to very large model, or it also applied to tiny model?
Yeah, in general, it's like the larger the model is easier to quantize.
Mm-hmm.
Yeah.
So have some actual experiments running on, for example, tiny models to see the effectiveness?
I think for 8-bit model, we also tried like 2-bit, 1-bit, 2-bit models.
Mm-hmm.
I think, 4-bit is difficult. I mean, if you want to, it depends on what's your goal, right? If you really want the real fast inference, like speed-wise, and you don't care that much about accuracy, right? It's all about trade-off, right? For smaller